Okay, so this is our very first lesson, our very first unit. Although it says Unit 3 in there because in day school I do the order a little bit out of whack. But for night school and summer school, it's always better to start with Unit 1, or single variable statistics as Unit 1. That way you have lots of time to get all your stats under your belt and then start working on your CPT right away. Okay, which is what's going to be important for night school or summer school. If this is day school, then Unit 3. Either way. We're starting with single variable statistics, and remember, these are statistics that we use to quantify and understand and look for patterns in a single measurement. Single variable. Just be a height. Or just be, I don't know, for something topical, an amount of people with COVID-19. Okay, or amount of new cases of COVID-19. That's just one variable. Okay, if you're going to look at amount of new cases with COVID-19 as time goes by, then you're going to be looking at a two variable stat. Okay, and you look at a graph that has both an x and a y axis and go from there. If we were just comparing countries and we were to look at the number of cases in Canada, which I think right about now is 20 or 30,000, and total cases reported, and then the number of cases in the United States, which is I think close to the millions now. I actually haven't looked at the stats recently. It's so depressing. But either way, you would be comparing and maybe making a bar graph of showing the United States, for example, and then Canada, and so on, and looking at the incidences, the different numbers that occurred for all the different countries for the amount of people who have been diagnosed with COVID, or I don't know, who have had car accidents, or who are within a specific height range, or how many men, or how many women, or whatever stat it is that you're looking at. Okay, so when we talk about single variable statistics, the first thing we need to talk about is the variable. Okay, and that's key. And we actually have to define the variable and understand a lot about the variable, so we don't just stop at that. Okay, but it's any measured quantity taken from a group of individuals. Okay, and that group of individuals that we take from is our population, and then who we take from that population is called our sampling frame. Generally, they should be the same thing, but if your sampling technique is not done effectively, then your sampling frame would be a little bit different than what your population is as a whole. But we'll get a bit more to that in later topics in this unit and our next unit. Okay, so again, a sampling frame is a group of individuals, hopefully your population that you intend to study or sample for the purposes of study. Raw data, of course, is just the straight measurements. Nothing's done with them. There's no patterns. They're not graphed. They're not organized in any particular order from greatest to least or whatever it may be. Just flat raw data. Okay, and it's this raw data that we gather, okay, from primary sources, which are actually measuring it yourself, or secondary sources, which is, you know, sources that relate to maybe stats that you get from a website or from a report or something. A lot of people who like their stats for sports will look on the official page of you know, the hockey NHLPA or MLB or whatever it is that you like to follow, and then you look at those stats there. That would be a secondary source because you didn't gather them and you know, log them through the game or whatever it is that you watch. And so a lot of the times those statistics are secondary sources. Okay, but whether it's primary or secondary, that's our raw data. Okay, so it's undigested. I call it digested because you haven't broken it down or simplified it or whatever, or unaltered information measuring your variable. Okay, sometimes we call a variable a parameter. Okay, it's another way to look at a variable, or another thing to call a variable is a parameter, a measurement, something that tells you something about a population. Okay, it can also be called a population of data taken from a population. We very often will use that terminology to talk about our data itself rather than to talk about the actual sampling group that we're taking from. So population or population of data. Okay, if this raw data is collected correctly, then it would give you a good view of your population. If it's collected with bias, then it's a bit different of a story. And we'll look at some information relating to that and diagnosis relating to that and some things that we can use to critically look at our data. Okay, but before we do that anymore, we have to look at the nature of variables. So what is it about our variable? Okay, because how we treat it varies depending on what the measurement is. Measurements can be all kinds of forms. You may remember from grade 9 science, a long time ago, that you talked about qualitative and quantitative measurements. Okay, qualitative physical properties and quantitative physical properties. So a qualitative physical property would be a state at room temperature, like solid, liquid, gas, or a color, or a texture, or things like that. And then you had quantitative physical properties like density, or I don't know, mass, or length, or width, or whatever the heck it is you're measuring for the particular object or chemical or whatever it was you're measuring. It was in the chemistry unit that you learned about it. Okay, so measurements can take on many forms depending on the nature of the variable that they measure. And this is the key. You have to focus on what the variable is, not what the measurements are, but what the variable you're measuring is. Is it qualitative or quantitative? Okay, is it descriptive or not descriptive? Is it numerical? And if so, what can those numbers be, and are all numbers possible? That's the critical sort of approach we take here. So this is just some examples. Okay, so the result of a coin toss can be a measurement. Okay, heads or tails, one or the other, that's it. And there's no number for heads and no number for tails, it's just heads or tails. So those are descriptions for situations, kind of like, solid, liquid, gas. Okay, when measuring preferred colors of a population, what's your favorite color? Probably when you did a little survey when you were in grade school to do some data management, that would have been something like that. Or what's your favorite sports team? Then all the answers would be descriptive, okay, or non-numeric. Okay, non-numeric in nature. If we're measuring the number of people that live in a house, that's different. That's definitely numeric. Some people have 5 people in their house, some people have 10 people in their house, some people have 2 people in their house, some people have one person in their house. Either way, those numbers are all numeric, but they're different than numbers that are measurements. Okay, so if we were to look at the birth rate of Canadian children, we could record any possible number. And so it's this analysis of qualitative and to quantitative, and there can be branched into all kinds of different types of data, okay, as we go from there, but these are the 3 focal points that we take. So one type of data that we have is called qualitative, okay, or another word, the word that your textbook uses, is categorical. Okay, categorical means that things fall into categories or groupings that have labels with them, and the labels are non-numeric. Okay, you can make numbers that are associated to them if you want to in some arbitrary scale, but the scale is not inherent in the definition. So it wouldn't be like color in the sense, if you're a physicist, because color actually corresponds to a wavelength and frequency of light, okay, in the electromagnetic spectrum, okay, whereas it is our perception of that color that gives it its name. So there's a little bit of a dichotomy in there, but color is a very good example of what we would call a qualitative or categorical data. Okay, because a categorical variable, because it is descriptive in nature. So these are some examples. But again, the measurements cannot be ordered in any logical or preferred fashion, and that's important because there's no definite order to color or religion or gender identity or, I don't know, nationality or, I don't know, political view. There's no actual value to be assigned to them. One doesn't go before the other. I mean, sometimes people do them alphabetically, but that's arbitrary. Okay, it has nothing to do with the actual measurement and how one comes before the other one and one comes after them. And so that's important, okay, because how we deal with them and the way we communicate them has to be done in a very specific scale, in a very specific fashion. So examples would be favorite color, yes or no answers, male, female. I shouldn't be binary there, so male, female, LGBTQ, whatever gender recognition that an individual has. They tend to fall still in descriptive categories. True, false, heads or tails, nationality, religion, all that sort of thing. Okay, those are all descriptive quantities. Okay, and we call those qualitative, for those of us who remember grade 9 science, or categorical variables. It doesn't make a difference, potato, it's the same thing. Okay? We also have quantitative variables. For quantitative variables, or numerical variables, we have 2 types. Okay, and then there was a big designation between the 2 of them. So this is something we really have to be sensitive to, and we really have to spend a lot of time on. I could just list out the definitions and go on, but this is an important feature that will be important all the way up to your very last unit that we do. Okay, so keeping that idea in mind, we do have to bring this home. Okay, now, these are variables measured with numbers where the measured values have an obvious and quantifiable difference between each other. 10 comes after 9 and before 11. There's a definite order to things. Okay, now there's 2 types of numerical data. Okay, one type is common but not as common, and one type is what we really think of as actual data, number crunching and stuff like in a science class. Okay, so there's continuous and discrete variables. Okay, and for those of you guys who took advanced functions, you know about discrete, continuous and discrete functions. Okay, so you'll kind of have a little bit of an understanding of this, but if you haven't taken it, you don't need to know it. Discrete means that you can have numerical values to measure things, but only specific values are allowed. You can't have anything in between them. So I gave the example of the number of people who live in your household. The number of people who live in your household can be 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10 or whatever. But you can't have 2.4 people in your household. That's not the way that it works. Okay, you have to have whole numbers of individuals. Now, discrete doesn't mean whole numbers, but whole numbers are very good examples. Like the number of Smarties that I get in a box. If I pour them out, the number of Smarties that I have is like 45 or 46 or 47 or 48. That would be discrete. Okay, only specific values are allowed. Now, you could take shoe sizes. That's a little different. You can have half sizes and whole sizes. If you have half sizes and whole sizes, you can't have anything between a half and a whole. Hat sizes, I know, go to 3/4 and all kinds of other different measurements. The point is that for discrete data, some values are allowed, some values are not possible. Doesn't mean that you don't see them in the numbers. You don't look at the numbers to tell you this. You look at the variable. You analyze the variable. So everybody's hat size could be all whole numbers. That doesn't mean only whole numbers are allowed. They could have halves and 3/4 and all that sort of stuff. But discrete variables means only specific values, not all the values in a spectrum, which is sort of in contrast to continuous variables. Continuous variables, again, are variables that have all possible values. So examples of these are the ones you tend to measure in science class, with a mass or with a balance or a ruler or whatever it may be. And these are things where all values are possible. Okay? All values are possible. So if I asked you your age, you could say, oh, I'm 18 or I'm 17 or I'm 16. But that's not accurate. You're 16. A certain number of months, a certain number of days, a certain number of hours, a certain number of minutes, a certain number of seconds, a certain number of nanoseconds to when I guess you just came out or they cut the umbilical cord or whatever the heck happened, okay, to allow you to be considered born or what your birthday was, okay? So that being the case, you can only, all values are allowed in this spectrum. So when you see continuous variables, you have to think of a shading from very, very dark to lighter, to almost not even shaded at all. And all values in between are possible. I haven't done a very good job coloring there. But you see whereas with discrete data, you're going to look at boom, 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 boom. Okay? And no values in between on that scale. Okay, and it's a really important thing to designate between the two of them. This is a nice little descriptor between the two. It talks about qualitative and quantitative data. So there's nominal data, there's ordinal data, and there's binary data. Okay, binary data is very often collected by human beings, whether it's heads and tails, pass, fail, up, down, things like that. Ordinal data tends to be sort of data that can have some order or greater than or less than. So blood grouping is a good one, A versus B versus O. If you remember the ABO system, if you took grade 11 biology, hopefully you remember that stuff. There's a little bit of a ranking of one versus the other versus dominant and recessive. Okay, and then nominal. Okay, there's variables with no inherent order. So there's degrees of ordering in qualitative variables. Okay, and degrees in which they could be classified, but generally that's the idea. For quantitative, again, we have discrete and we have continuous. So have a quick read of that and look at that scale and get to know it really, really well. There will be a question also on a survey I want you to conduct at home. And in that survey I want you to conduct at home, you're actually going to go over a bunch of measurements in just some silly survey that I gave you. And in those bunch of measurements that I gave you, you're not only going to look for sources of bias and things like that. As we go through this unit, we'll learn about this stuff. You're also going to learn about discrete and continuous, and you're going to have to label each measurement and whether it's discrete or continuous or categorical. Okay, so make sure you understand those fairly well. And there'll be some things to go over in your homework questions and stuff. Okay, so that's the nature of our measurements. Now let's actually start getting into crunching our numbers. Now, the crunching that we're going to be doing is nothing too crazy, but it is something that we're going to do. Okay? So this is the analysis of single variable data. The first type of analysis that we tend to look at, which is the very common, is something called frequency. Okay? How often does it occur? How often do we see it? Okay, so I guess you could look at the frequency if you're looking at the data for the number of people who enter at Tim Hortons and the number of coffees that they order. Now, that would be an example of discrete data, because you can only order 0 or 1 or 2 or 3 or 4 or 5, all the way up to, I don't know, 10 coffees, okay? And so as a result, then you can only have specific values, but you probably have some values that happen more frequently. Maybe the most common thing is 4 coffees or 2 coffees or 1 coffee. I don't know what the most common is. So you look at the number of times 1 occurs where a person orders 1 coffee, and the number of times 2 occurs where a person orders 2, and so on, and you look at the frequency. Okay, and that's the very first sort of measurement that we have for single variable stats. How often does it occur in the data set? Okay, and then of course there's different types of frequencies. So we'll look at those different types of frequencies as well. Okay, so if you look at this as an example, okay, frequency, the number of times a particular datum appears in a data set. That's the frequency. So this is an example. We roll a single 6-sided die. We roll the dice and we record it. In this case, we roll it 1, 2, 3, 1, 2, 3, 4, 5, 7, 8, 9, 10 times, 10 times 3, 30 times. So 30 rolls of the dice. Okay, and these are the numbers that we got, single die. Okay, obviously they're discrete because you can only get a 1 or a 2 or a 3 or 4 or 5 or 6. Okay, so rolling a dice is going to be a discrete outcome, but it's numeric because we count the number of little dots or pips on the dice. Okay, so if we were going to go ahead and do this, we would go ahead and do a frequency table. Okay, to summarize this, and you probably remember doing this when you were a little kid. Okay, so you'd go through the 1 and you'd be like, okay, got 1, and so you put a little tick mark in there, and then another 1, boop, tick mark in there, and then the 4, tick mark in 4, and then a 4, tick mark in 4, and then a 6, tick mark in 6, and then a 3, tick mark in 3, and so on 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 and so on. Eventually you'd boil down to the number of values that are actually there. I'm going to use a little cheat here because I think that hopefully we know how to calculate or how to count. Maybe I'll finish the line. So 3, I put a tick mark in 3. I get number 5, I put a tick mark in 5. I get number 3, I put a tick mark in 3. I get the number 4, I put a tick mark in 4. I get the number 1, put a tick mark in 1. So far, we haven't even seen a 2 yet, okay? And the most frequent is a 4 and a 1. Now, we know that this is a single 6-sided die. If it's not loaded, then it should be perfectly balanced, and so we shouldn't see any problems. And as a result, it should be nice and even for all of them, but that's probability. We'll talk about predictability and stuff like that later on. Right now, we just want to crunch the numbers. So if you want to, you can continue all the way along here and all the way along here. The results that you're going to get, I've got my cheat sheet. You've got these on your notes. So if you're following from these notes that you've printed out, that's great. It's a good idea to follow from these notes and to follow the lectures along with them. They won't always be the same, but they do have some extra little notes and stuff in different colors that'll help you figure things out. But let me just write these down in sheet 5, 5, 7, 4, 4, 5, totaling up to 30. Let me count. 15. 15 is 36 plus 4 is, 26 plus 4 is 30. Okay, so that's correct, all right? And it's always good to sum things up just to make sure. Most people don't sum the tallies, okay? But either way, that's a frequency table. Now we call it a distribution. The reason why we call it a distribution is because it shows how the frequency is spread out amongst all of the possible outcomes, all the possibilities. All the possibilities are 1, 2, 3, 4, 5, 6. And we can see that the most common outcome is 3. And we can see the least common outcome is both 4 and 5. And then we can see sort of the middle outcomes are going to be 1, 2, and 6. So it's a distribution because we're looking at how the frequency is distributed. And I expect you to use that language on your titles for your graphs. Okay, so this is a frequency distribution table, and then logically what we would do after that is we would make a graph. Now they generally tend to be bar graphs. We'll talk about different types of graphs at the end of this section here. But this is a frequency distribution graph. Now you notice in the title I've got frequency distribution showing the outcome of a series of rolls of a single 6-sided die. So I've got frequency distribution of the datum, and then I talk about maybe some conditions about where the data came from. Okay, in this case, a roll of a single 6-sided die. Here we've got frequency. That's our only real measurement statistic that we have here is the number of times it occurs. Okay, and then down here we always have what we call our random variable x. In this case, our random variable x is the roll. Okay, so that's the outcome, the roll. The y is just this single measurement that we take, this single statistic. Okay, in this case, frequency. Okay, now, very often frequency can have a lack of meaning depending on whether or not we know the size of the whole. Okay, so if a datum appears 5 times, like for example the number 1, that would be, maybe a lot, maybe not that much, maybe we don't know. In a data set, this could be significant, expected, or even insignificant. If we roll the dice 1,000 times and we got 5 1s, that's significant. If we roll the dice 5 times and we got 5 ones, that would be significant. If we roll the dice 5 times, if we get 5 ones and we roll the dice 30 times, it's completely expected because 5 out of 30 is 1 out of 6, 6 sides, nice evenly balanced dice, and you would expect that's what the probability would be. Okay? So very often we don't just look at raw frequency. We look at raw frequency in a distribution in comparison to the whole, or we look at a different measurement of frequency. We take the frequency and we scale it to a specific size. Okay? We index it. Okay? And when you index something, you make it a per. Okay? And that's a very important thing because, as you can see, Donald Trump says we do the most testing. We do the most this. We do the most that, all the way through the COVID testing scenario in the United States. But what most people really should be interested in is the amount of tests per capita, the amount of tests per person in the population. And that's an indexed value. It's a more accurate statistic because it allows us to compare statistics to each other. So if we look at the amount of tests in Canada, of course the amount of tests in Canada is going to be less than the amount of tests in the States because the United States has 10 times the population size. If you look at the amount of tests that have been done per person, scaled to the size of the population, it's a bit more significant, the amount of tests that have been done. And so Donald Trump doesn't use that statistic, A, because he probably doesn't understand statistics very carefully, and B, because he doesn't want to really tell us the true numbers. Okay, because then that looks like maybe he didn't do a very good job, or his government didn't do a very good job in taking care of the American people. Okay, so that's why an indexed value or a scaled value is very important. So a relative frequency is a frequency measured compared to the size of a whole. It's usually talked about as a percentage, because a percent is usually out of a whole, or it's talked about as a value between 0 and 1. Okay? And as a result, we see a value between 0 and 100% or 0 and 1. Okay? But it's the frequency divided by the whole. We do have another type of frequency that can be kind of important. It's actually very useful in finding some of our measures of central tendency. And that is something called a cumulative frequency. A cumulative frequency is a running total, okay, where you look at the frequency of different occurrences, generally from greatest to least, but if it's categorical data, you won't have a greatest to least. But what you'll do is you'll look at the amount of individuals that actually have been sampled that fall into that category. Okay, and so what it does is it tells us different things. So I'll come back to that, show you how we calculate it, and then show you what it means to you. Okay, so first we've got our old table. This is the table from the previous one. Okay, and we've got frequency. Okay, frequency, remember we had tally. I'm not even going to bother with the tally, okay, because we've already done that. It's already, I don't even think I've bothered from it in your beautiful notes. No. There, okay? But I do show you how to calculate the new ones. Relative frequency, all you do is you take your frequency and you divide it by the whole. So 5 divided by 30, okay, 5 out of a total of 30, which is 0.17 or 17% if I round it, because it's 0.16666 repeating. But it's 0.17 if I round it, or 17% approximately. Okay, same thing for 3, okay, 7. Frequency of 7 out of a total of 30, and so we see about 23%. Okay? And either way, all of these will either add up to 1, or if you can express them as percentages, they'll add up to 100%. Okay? And that's a relative frequency. That's a much better measurement. It's also something that we call experimental or empirical measured probability. Okay, in that data set, if we treat that sample as a representation of the entire population. Okay, and we can actually use it as a predictive feature if we want as well. Okay, so that's empirical data or measured probability. Okay, so relative frequency is a very, very important stat. Okay, cumulative frequency is kind of interesting because what it tells you is it tells you the amount of individuals who have that criteria or the one below it. So cumulative frequency generally tends to be used for quantitative data. And so if you look at, for example, the number 3, if I look at across 3, the cumulative frequency is 17. Has nothing to do with the 7, and the fact that it's 17. It has nothing to do with the 7. What it tells me is that's another number of people. The cumulative frequency for 3 is the number of times, or number of rolls in this case, that had a 3 or a 2 or a 1. If you take the 17, let's go back to this frequency. If you take the 7 and the 5 and the 5, all of these, 3 or below, add up to 17. That's what the cumulative frequency is. So the cumulative frequency for 1 is the same as its frequency. Why? Because you can't have anything below 1. So this is 1 or below Well, there's 5 people because all you can get is a 1. You can't get lower than a 1. But if you look at 2, the cumulative frequency is 10. It's the number of individuals that got a 2 or a 1. Okay? And if you take the 5 and the 5, it totals to 10. If you look at number 6, which is the highest value that you can get, the frequency is 5, but the cumulative frequency is 30. Because that's the number of people who got 6 or 5 or 4 or 3 or 2 or 1. And it adds up to the total. Okay, in this case, the total is not applicable, but the total of roles is 30. Okay? And then, of course, we can take the relative frequency and the cumulative frequency, and we can also put them into these bar graphs. And I expect you to be able to use these bar graphs, and I'll talk about some features relating to them. Okay, so again, these are roles. Okay, there's a couple of things that we'll notice in a second, but first of all, you'll notice in the title, relative frequency distribution. And over here, it's relative frequency. You'll also notice the scale here goes from 0 to 0.25, so it's only going to be a decimal value, or you could use percentages if you wanted to. And you'll notice that this graph looks very similar to your previous graph. Okay, the previous graph of raw frequency, has the same sort of bump and then bump pattern, exactly the same pattern, although the numbers are a little bit different. They correspond a little bit differently. Okay, and here is a cumulative frequency distribution, again included in the title, and then a little bit about what the actual variable is. Okay, so you have to have a nice, well-rounded out title. So a cumulative frequency distribution, you'll notice that it starts with the lowest value, in this case 5, and it pops up and pops up and pops up and pops up and pops up. We don't generally tend to look at cumulative frequency distributions too often in ways in which to understand the distribution of data in a sample, but it's there, okay, and it is something that we should be able to do. A couple of footnotes. Remember, this is my value, okay, of my role. You have to define that random variable x, so this is your x-axis. Those are all the outcomes that you can have. Now, one thing that you'll notice for this is that there's spaces between the bars, and that's going to be important because this is discrete data. It's a roll on the dice. Because it's discrete data, there's spaces between number 1 and 2. You can't get a 1.5. So we don't fill in the dots like we would if we were connecting the dots for a function in grade 11 or grade 10 or grade 9 math class. Okay? What we're doing on this graph is we're separating them and actually putting spaces between the bars. And those spaces exist because there isn't a continuum between 1 and 6. There's 1 and 2 and 3 and 4 and 5 and 6, and that's it. Okay, so it's discrete data. So that's something to keep in mind. That's pretty important. Now I'm going to stop here. Okay, I'm going to go through some more, but I don't want to make the video too long. I want to give you guys a bit of a break. So I'm going to give you a bit of a break here. Let me stop the video.